very glad to have Varadhan here. You're so okay today. Particle systems, conservation laws, big solutions.
Thank you, Shiva, for inviting me, and I'm always happy to come back to my first home, which is ISI. And I was told that this is a student seminar, so I chose a topic that's fairly elementary to describe. So it's particle systems, conservation laws, weak solutions, and entropy. A particle system just means a whole bunch of particles, like molecules in this room or something like that. And conservation laws means although these particles interact, their interaction changes some things about the particle, but certain things don't change, certain things are conserved. For example, if the particles are not destroyed or created, no matter what they do, the number of particles does not change. So the density of particles is a conserved quantity. Or if it's Newtonian mechanics, the interaction, the momentum is conserved. So the average momentum is sort of conserved. And total energy is conserved. So there are various conserved quantities. And they're important because you don't want to keep track of all the location of all the particles. In order to describe what's happening in this room, technically Newtonian mechanics says that if I give you now the location, exact location of each and every molecule in this room, you should be able to compute its location at any future time. In practice you can't do it, right? But on the other hand, if you know the direction in which the wind is moving, which part of the room is hot, which part of the room is cool, or there is a high pressure of gas, or is relatively empty, then you can say about how the whole gas system will move. And this is what conservation laws are about. They tell you how variables which are bulk variables behave when you specify only how the smallest scale. So variables are, you describe only the system at the microscopic or micro, the lowest level, but you ask questions about a much higher level, and how do you derive those equations, and that's the issue in general. And what I'm going to discuss today is a very simple example of it. You can think of it as driving in a car in Bangalore. Okay? Let me describe the model. Maybe I should use a chalk just to begin with. Okay. So there are these sites. There are these particles, which you can think of as cars if you like. They all want to go in the same direction. There is only one lane, and you can't jump over anybody. So you can only move if there is an empty space. If there is no empty space, you have to wait. That's a model which is called totally asymmetric simple exclusion process. Okay. So the question now is, if I take such a system, I start initially at some configuration. I don't care exactly where the particles are located, but I take a picture from very far away, so the entire integer becomes continuum, because it's from very large scale. The distance between these 2 points become very close, so it become a continuum. And I count the particles in some way. What I have is a density of particles rho which lies between 0 and 1. Because in a given volume you can have at most one particle per site, so in some normalization the density is between 0 and 1. So I give such density at 0, and this is rescaling, so somehow this entire thing length is divided by n, shrunk, and the ratio calculated to compute the density. So there is a scaling of n. And similarly time has to be scaled by n, and you look at it at time nt. Then this density rho, which is given at time 0, will evolve to a different density at time rho t. And the problem is, how do you derive what rho t is in terms of what rho 0 is? You have to define a differential equation of some kind, and an initial value problem for a partial differential equation, which will tell you how to compute rho t in terms of rho 0. That's the issue. Okay. Of course, one of the problem is this equation is not a linear equation in general. It's a nonlinear equation because imagine everybody is moving with a constant velocity, then you can imagine that d rho t by dt will be, it's a function of two variables, the location variable and the time variable. That will be something like d rho dx. That corresponds to moving with unit velocity somehow, right? Just streaming with linearly. But now, here, the rate at which particle can move depends on the density. You know, if it's midnight in Bangalore and the density is very low, it can go very fast. But if it's 10 o'clock on a working day, the density is high and you have to go slow. So the density is, there is a coefficient here, so the actual equation would be some density times some speed times sub x. And the speed is a function of rho. And that makes the equation nonlinear. So what you have is a nonlinear partial differential equation, and handling it is a little difficult. Then the question in PDE theory, either the solution may have smooth solutions, or you may have to take weak solutions for this, and the weak solutions may not be unique, and you may need extra conditions to get a unique solution. There are complications that arise. So what we are going to study is just what are all the complications that can arise from this very simple model. Just to give an idea of what the subject is about. So this is simple exclusion process in one dimension. So the notation is eta is a configuration. Configuration means for every site on the integers, you have a variable which is either 0 or 1. 0 means that site is empty, 1 means that site is occupied by a particle. So and simple exclusion means you cannot have more than one particle at the same site. So there is at most, so each site is either empty or has one particle. Those are the only alternatives. And a particle can jump from its position to a new position with rate lambda z. What does rate lambda z mean? It's a Poisson thing, and in an interval of length time delta, it can jump with probability lambda z times delta from x to x plus z. But for this to happen, two things must be satisfied. First of all, there must be a particle at x so that it can jump. If the site x is empty, nothing can jump. And site x plus z must be empty so that the particle at x can jump to the site x plus z. So under these conditions, with this rate, you can jump from x to x plus z, and the new configuration is denoted by eta with a super xx plus z. That means you can define the configuration as one in which nothing happens at points other than x and x plus z. At x and x plus z, you do a switch. And that's the new configuration, eta super xx plus z. And this is in fact a Markov process, because all I have is certain transitions and I specified the transition rates. So you have Markov process, and you should be able to write down the infinitesimal generator for it. And there are two alternatives at this point. Either you can take the state space to be all integers, or you can wind it around in a big torus, a big circle, with at least n sides, so that when you scale by n, you get the unit circle. So it's, either one is essentially the same problem. So this is the generator. All the generator does is it lists all the things that can happen and at what rate they happen, right? So you are evaluating a function at the new configuration minus the old configuration. It tells you the changes from eta to eta x plus z. It tells you for the change to happen, eta x should be 1 and eta x plus z should be 0, otherwise this whole thing is not there. So that tells you that thing. And then there should be, this tells you the rate at which this happens is lambda z, and then you sum it over all x and z, and that's your generator. And the summation here, z is over, in the simple exclusion case, z will only take one value, 1. All the other values will be 0. That means the only possible jump is to the right one step. Otherwise, you can jump forwards and backwards. And the summation over x is over all the sides. Could be either all the integers or all the integers, n integers arranged periodically in a circle. Could be either situation. So if you want to compute the expected value of something at time t, given that the system starts at some value at time 0, this is the configuration of the system at time 0, and you want to know what is the expected value of f evaluated at the configuration at time t, that's the equation you have to solve. That's just the semigroup equation, which tells you that f is the infinitesimal generator is this operator A, and you have to solve the equation d dt equals AF sub f. So how do you compute the density profile of something? Well, you compute it by taking a test function j and then summing it, weighting it by eta x. So you're just summing jx over n over all the sides where there is a particle. And you normalize it by 1 over n, and the limit, if it exists, gives you the density profile. Since eta x is just more 0 or 1, the rho can be only between 0 and 1. This limit doesn't have to exist. But if it exists, then you say there is a definite profile, because it can vary very wildly so that there is no profile. So having a profile means this limit exists. So you can have either z or zn that will lead to, in the limit, the integration could be over r or over the circle. For time 0, there is a profile rho 0. Can we say that there will be a profile at time nt with probability close to 1, and can we describe it? And that's the problem we have. time is nt because we assume that z pi z is positive, so the particles want to move to the right. Even if some z negative values of z are possible, on the average it want to move in the right direction, and that means it's moving at some speed, and therefore in time t it will go a distance proportional to t. Since the space has been normalized by dividing by n, in order to get something meaningful, the time should also be normalized by the same scale. So you want to speed up time by n. So what you want to compute is really this derivative. So here is what the profile at time nt wants to be, and you want to see how it changes. And you know how to compute it. It's you just calculate the infinitesimal generator applied to that, and then I have made one simplification here. I should have j of x plus z minus j of x, because the effect of a jump is moving x to x plus z. J increases or decreases value from jx to jx plus z over n. So it's really z over n times j prime x over n, but I have speeded at time by a factor of n. The two n's cancel out, so you get this. Now, here I am making a crude assumption that if the density is rho, then what does it mean? That means probability of finding something at a point is rho. What about the probability of finding some point here and some point at some particle at the next site, or finding the next site empty? The next site empty is 1 minus rho. Finding something here is rho, so the combination should be rho 1 minus rho if they are independent. I'm going to assume they are independent. Okay. So if you assume they are independent, then the expected value it's going forward. How to go backward here? I need to go backward some more. Can I go back on this? This one?
Yeah. That's the that. I'll just press this guy.
Okay. Thanks. So what you need to compute is this. Okay. So this quantity, I'm going to replace this by rho times 1 minus rho, pretending the two are independent, and if I want to take an average, I can do that. So the equation becomes, if you do the averaging, j prime rho 1 minus rho. Now I can remove the test function, do a little integration by parts, and I get this equation where m is the expected value of pi, summation z pi z. So this is the equation which is called Burgers' equation, which describes the motion of the density in the system. Now the question is, does this have, now how do you justify this? Okay. So what you need to know is, why is, imagine the system in constant density. A system in constant density, you can check, is in equilibrium in some sense. It should not change in time. There should be an equilibrium with constant density, which should change in time. And in this case, you can verify that the invariant distribution for a system with constant density is just the Bernoulli measure with density rho. So what you expect is locally your system should be nearly Bernoulli, but at different points due to different densities it will be Bernoulli with different rho. So at two neighboring points they are independent with probability rho 1 minus rho, but the rho itself could vary from point to point. But if two points are close by, it shouldn't vary by much. You have to go at least point of order capital N to see any real difference. And that's the philosophy behind it, and that can really be proved with some analysis. So if you buy all of that, then this is the equation we have. However, we don't have a smooth solution of this equation, we only have a weak solution of this equation. The question is the weak solution unique? One can use PDE theory to some extent and show that a smooth solution is unique. But are there non-smooth solutions to this equation? Okay. M is just the summation z by z. And in the TASEP case it's just 1, because you only move to the right with probability 1. Weak solutions is not. For instance, I have two solutions here. Rho is 3/4 for U positive and 1/4 for U negative. And it's 3/4 for U negative and 1/4 for U positive. Rho 1 minus rho in both cases is 3/16. And its derivative with respect to x is 0. So its derivative with respect to t is 0. So they are both weak solutions. Right? So how do you interpret it? You think of it as traffic, somehow a discontinuity in density is traffic jam. So what this situation describes is a traffic jam. And the first one is there is a traffic jam because there is heavy traffic ahead of you. This is a traffic jam because there is heavy traffic behind you. Which is realistic? When there is traffic jam, when there is high density ahead of you, it's more realistic. So it's the first one which is the real solution, and the second one which is the fake solution. And you need a method to distinguish between the two. Okay? That's where entropy comes in. So in both cases, which is the real solution, the entropy condition comes in. So the entropy function here is h of rho is rho log rho plus 1 minus rho log 1 minus rho. And its derivative you can compute is h prime rho times rho t. Rho t is that, so you can write it like that. And then you can simplify what h prime rho is, and you can write it as in this form. So h rho also satisfies a conservation law of some type. So if you integrate over u, this tells you that h rho is conserved. If rho is a smooth solution, the entropy is conserved. Okay. But in a non-smooth solution, what happens to the entropy? It changes. Some types of discontinuity, it goes down. Some types of discontinuity, it goes up. You have a question?
What's G?
G is such that its derivative is 1 minus 2 rho log rho over minus rho. Just work backwards. in general, if you have a system, a Markovian system, and if you have an entropy of some sort, you can check that this entropy is really the entropy in the usual sense. You know, if you have a distribution, for example, compute the entropy, basically this is what you will get. So this is standard entropy. So the entropy of a system should decrease. That's any Markov process. If you compute the entropy related to the invariant measure, it's always decreasing. So you don't expect it to increase, but it's possible that at some places it decreases maybe. But one can show that the limit that appears as a weak solution, it's always decreasing. But one has to view it carefully. I describe for a jump what it means. Okay? It should be decreasing, but you can check that, you know, you can translate H rho decreasing as 0 increasing. G is monotone, 0 increasing means rho must be increasing, so across the jump rho must be more on the other side and less on the back side. That's the interpretation. The mathematical theorem is a weak solution is unique if it satisfies the entropy condition. We did the entropy condition for one special convex function, which is rho log rho plus 1 minus rho log 1 minus rho. But the general entropy condition must be satisfied for every convex function. But there is a theorem due to Felix Otto which says if it's valid for one strictly convex function, then it's valid for every convex function. And in our case, entropy is strictly convex, so it's okay. But in general, if you don't know that your solution, the weak solution you have, has just jumps, who knows what kind of horrible discontinuities it has. So you just can't talk about jumps. It may not even have limits at every point. So what you need to do is think of this quantity, nu is h rho sub t plus g rho sub u. You can think of it as a distribution, because h rho and g rho are well defined, so the derivatives are distributions. So this distribution should be non-positive as a distribution. That's the real entropy condition. Under that condition, you have uniqueness. That's the theorem. Okay? And that will give you the right condition for jumps automatically. This translates to require that the follows from the monotonicity of 0. Thus, Bangalore has proved convergence to a limit in more general situations. Okay. Now, can the measure be of bounded variation? What if it's not non-positive, but it's just a signed measure of bounded variation? Then it is not the weak limit, but does that fake solution have any meaning? Is it relevant in some way? Since the total entropy is a bounded function, so the total measure of the signed measure is always bounded. So if mu plus is bounded, mu minus is bounded, and if the total variation is bounded, it's all the same thing. Okay? So if mu plus is bounded, then mu minus is bounded as well. Because the sum of the two you can control. So let's say mu plus is finite, not zero. There are many such weak solutions. Do they have any role to play? That's in fact the large deviation rate function in some sense. Okay. What does it mean? Particle system, when scaled, you want it to be close to rho, that's not necessarily a solution. That probability will exponentially small. It will be e to the minus n times some constant, approximately, constant depending on rho. There will be the rate function for large deviations. And so what do the large deviation look like? If rho is not a weak solution, then the rate function is infinite. So the rate function only lives on weak solutions. And on weak solutions, the rate function is just nu plus, v nu plus. So that's a complete description of not only the law of large numbers, but also the large deviations in this case. And if it is not a bounded variation, then again the rate function is infinite. If it's a bounded variation, then the rate function is just nu plus. This and much more is in fact known for TASEP. See, we just did now the law of large numbers and large deviations for this. But then there is a whole lot of things in between fluctuation theory. You can study fluctuations of various things. Okay? And the question is, how do they behave? And they have been very well studied, and there is a whole body of literature with various connections to random matrices, Tracy-Widom distributions, many other exactly solvable models. These are known. Connections with KPZ theory and so on. So the fluctuations of this model have been very well studied, and there is a wide literature. But these are all arise by exact computation. There is some complicated formula of Tracy and Widom that can be analyzed in order to extract information about them. Now, there are other natural questions one can ask for which the answers are not known. So let me describe some of them. One of the issues you want to know is in TASEP, or even in TASEP, if I remove the T, that's ASEP, and that means pi z, the mean is positive, but pi z can be positive for z's other than +1. That's ASEP. And just plain SEP means its pi is symmetric so that the mean is 0, and that's totally different situation. Okay. So you can ask the following question. What can you say about the location of, what did I chalk? I'll take a new one. Here it is. Okay. Can I ask the question in this model? Suppose there is one particle which I tag. I want its location. Where is it going to be after time t? Well, if it stays up, it has no room. It's locked in. So wherever the flow takes everybody, it's going to go there. Okay. On the other hand, if things can jump, then it doesn't have to be bound to all the other particles. It can sort of go its own way. And if it's in equilibrium, if you start initially in equilibrium, that means you start with probability eta x equals 1 is rho and make them independent, start with that initial configuration at any point not equal to 0, and x equal to 0, you put a tag particle and you follow the motion of the tag particle. If you want to know how it's going to move, then at any time, if the tag particle here, it's going to see that will be its expected motion, because it can move to all, potential move to all the empty sites, and however many empty sites it sees and where they are located will tell you what its local mean is. And you want the average of this over a long time. That's what the actual motion is. But that means you have to know what the invariant measure for the tag particle is when it in its own environment. What is the average environment the tag particle will see? That's what's needed to compute this. And in these models, one can prove that the environment the tag particle will see is the same as the original environment. So long as you have that, this motion can be studied and it gives you the same answer. So what if the tag particle is slow? Now if it stays up, you are stuck here and an old lady driving very slowly, you're going to be stuck for a long time. So a slow particle can slow everybody behind it. So what kind of environment will it see? The environment it sees will be more or less empty space in front because everybody else would have speeded away, and a lot of high density behind it somehow. Okay? So changing the motion of just one particle will change the entire invariant measure, and it's not exactly computable in many situations. There are a few situations where it can be computed and then you can get exact answers. Otherwise, it's even difficult to show there is a unique invariant measure for this. Okay? So these are difficult problems for which there doesn't seem to be an explicit answer so far. Or you can ask other questions too. What if the environment is moving at some speed m, but the tag particle has no inclination to move? It likes to go in either direction with equal probability, but the flow might still take it along. Does that happen? Does it happen with linear speed, or does it happen with reduced speed? Those are things that one doesn't know. Or another question is, what if two types of particles? So at any site you have a particle of one type with density ρ1, a particle of second type with density ρ2, and a particle of the third type with density 1 minus ρ1 minus ρ2. You start with that configuration with both types of particles mixed, and then this wants to go with one speed and that wants to go with another speed. And then what will happen? It's not clear. They affect each other. The net answer is, again, it depends on computing the invariant measure. And the invariant measure for these models, you know it exists because of compactness, but you don't know what it is, you don't know if it's even unique, or there are several. a more interesting example is when they want to go in opposite directions. Okay. If they want to go in opposite directions, they are both in TASEP. It's like two cars in a blind alley going in opposite directions. They meet, they don't know what to do because neither of them can back up. Stuck. Right. So if you're going in opposite directions, you have to allow room for backup. Just giving an opportunity for them to jump over is not enough. Because if you give them just an opportunity to jump over 2 steps, you can have not just one particle, a group of 4 and a group of 4 blocking each other, and then they're stuck. So to become unstuck, you have to be able to step back. So give them, so let pi z be both positive for both positive and negative values of z, then you have an opportunity for them to step back. But that's no guarantee that they will successfully negotiate and go through each other. Because, depending on how strongly they want to go forward and how high the density is, it takes a long time to unwind this. Meanwhile, there are other particles which are streaming along. And so there is a competition between new particles coming in and the particles trying to create room. So if the density is high, my guess is they'll get stuck. Or if the push towards going is too greedy, then again they'll get stuck. If it's not too greedy and if the density is low enough, they may be able to negotiate their way through each other. So I expect there is some kind of a phase transition there, which one should be able to analyze. But I have not much success in proving any of them. Okay. Thank you. Two dimensions is borderline. Not much is known about 2 dimensions. 3 or more dimensions is easier to handle because there one can do things. Perturbation works because of the transience of various things. 3 dimensions is a lot easier. 3-dimension one can analyze to some extent. They are not explicitly known, but there's more room to wander around and go, so it's not a issue.
So even the one-dimensional case, has there been some simulations to see what happens?
Yeah, we tried simulations, and these conjectures are based on simulations. When the density is low and you just give them a slight bias, it doesn't get clogged. But if you increase density or you force them more, then they do get clogged. The similar phenomena happens also in random trees. If you have a random tree and you want to give it a bias away from the root, and you want to know how far it goes, if you push it too strongly, then it will go to a dead end and get stuck. So it doesn't necessarily take the long route. So similar things happen on other places too.
When you're discussing tag particles, you're saying that if something happens, if it is slow, then it can affect the whole system, the evolution of. I mean, an individual particle not supposed to affect the whole.
No. See, the point is, it affects the whole system in the sense that just think of you're driving along, okay, in a single lane road. Everybody is moving comfortably. The guy in front of you has a breakdown. He has to stop, so that affects the whole system. It doesn't mean your car is not in running condition. Your car is in the same condition as it was before. But you are not able to move because in order to move you need an open slot. The fact that the open slot is no longer available affects you.
The probability of that should be small for it to not affect the whole system.
Breakdown of an event is,
Slow vehicles, your car is there, then everybody has to slow down.
whatever the probability is, the model assumes there is one car that suddenly has a slow rate. Maybe it happens once in 10 years, once in 100 years, whatever it is, what happens when it does happen. The effect will be to stall everybody else.
Okay, there are no